Welcome to today's Explainer, everyone. Today, we're diving into a truly groundbreaking meta-analysis, one that absolutely shatters the age-old myth that you're either born a natural math person or you just aren't. We're going to unpack a massive piece of research by David Uttal and his colleagues from the Psychological Bulletin. It fundamentally changes how we view human potential, specifically when it comes to spatial skills and their absolutely crucial role in STEM fields. If you're at all interested in education, cognitive development, or, just figuring out how we can actually build more engineers for the future, you are gonna love this data.
So why exactly do so many students struggle so much in science and engineering? Well, we usually just blame a lack of foundational math skills, right? Or maybe poor verbal abilities. But recent long-term studies looking at nationally representative samples have actually shown that spatial ability is a massive, unique predictor of achievement in STEM. And that's even after you hold math and verbal skills constant. It turns out spatial skills might just be the missing link, the hidden gatekeeper.
Section 1, the STEM spatial connection. This connection leads directly to a very real-world crisis, which researchers call the catch-22 of early STEM learning. Think about it. When students first start out in chemistry or geology, they have to mentally manipulate complex molecules or 3D rock formations in their heads. If they don't have strong spatial skills right at the starting line, they literally lack the tools to visualize these concepts. They get super frustrated, and a lot of times they just leave the major before they can master the subject. And the cost of that frustration? It's steep. To put it in perspective, in places like Ohio Public Universities, over 40% of students who declare a STEM major end up dropping out of the field before they even graduate. These are highly qualified, genuinely interested students who just hit a brick wall. Section 2, defining spatial skills with a new typology. Okay, historically, the definitions around spatial skills were pretty messy, but this research elegantly breaks human spatial thought down into a really neat 2x2 matrix based on cognitive research. Up on the top, we have the difference between intrinsic, which is looking at the parts within a single object, and extrinsic, which is the relationship between different objects in an environment. Then on the left side, we differentiate between static, meaning the information is fixed, and dynamic, which involves some kind of movement or transformation. So for example, just recognizing that an object is a rake is intrinsic and static. But mentally rotating that exact same rake in your head to see if it'll actually fit into your overstuffed shed, that is intrinsic and dynamic.
Section 3, the power of training and testing malleability.
For decades, there was this really persistent myth that spatial skills were strictly fixed at birth. You either had them or you didn't. Well, to finally put that to the test, researchers analyzed a staggering 217 studies. After they cleared out the outliers, the meta-analysis found that the average effect size for spatial training compared to a control group was 0.47, which is huge. That means with the right training, spatial skills can improve by nearly half a standard deviation. This proves completely, unequivocally, that spatial skills are actually highly malleable.
Section 4, durability and transferability.
Now, skeptics will usually jump in here and argue that spatial training is just a fleeting trick, right? That participants are just getting better at the specific test they're practicing on, and it's never going to transfer to real life. But these findings totally shatter that argument. The improvements you get from spatial training are highly durable over time, and they are completely unaffected by delays between the training itself and the post-testing. But even more impressive, the training transfers to entirely new, untrained spatial tasks. And crucially, this malleability is effective across both males and females and across different age groups. We are talking about a permanent, transferable cognitive upgrade. Section 5, educational implications and building more engineers. Let's connect all this cognitive psychology data back to the ultimate payoff, actually solving our national shortage of STEM workers. We know that engineers typically have spatial skills about 1.58 standard deviations above the general population. Well, if we take a highly conservative estimate from the data, just a 0.40 standard deviation shift from training, and we shift the population curve slightly to the right, the area under the curve at that specific engineering threshold literally doubles. We could double the number of people with the baseline cognitive spatial skills required to become engineers. Just let that sink in for a second. For way too long, we've treated spatial skills like some kind of innate lottery. We've just passively watched students drop out of STEM because they hit a spatial visualization wall. But the data is loud and clear. These skills are highly malleable, they're durable, and they transfer. So instead of passively asking who is naturally good at STEM, shouldn't we be actively asking how we can train our students for it? Thanks so much for exploring this amazing research with me today.